When we first start thinking about torque, it's helpful to relate this back to real-world phenomena. In general, fewer aspects of rotation are things that we're familiar with, but torque you do know something about. Think about trying to close a door. This is a top view, the hinge is on the left, and you know that you can push so hard. From your everyday experience, you know that if you push directly on the end of the door, that the door is not going to close, that nothing will happen. So that one's bad. You know that this one, if you push really close to the hinge, it's only okay. If you go near the end of the door, but you push at an angle, that's good, not great. But then if you push near the end of the door straight on, that's going to be the best. So how does this relate to torque? What you're actually trying to do is make the door rotate around the hinge. So this isn't actually about force, right? Because in all of these cases, the forces are of the same magnitude. So we see that where we place the force on the object and what angle we place the force makes a big difference. So this is going to influence torque. Torque actually, it depends on both the force, where it's placed, and what its angle is, and hopefully the door situation is one that you can relate to from your everyday experience. To calculate torque, you need three things. You need the radial distance from your pivot point to where the force is applied. You need the magnitude of the force that's being applied, and then you need an angle. And it's really tricky to get this angle right. This is really important. It's not this angle, the angle that your object makes with respect to some axis line. That isn't the angle at all. The angle that goes in here is the angle your force makes with the positive radial line. So what that means is if your force is perfectly perpendicular, phi, or phi, is 90. If you're pulling in a radial direction, that's 0, and sine of 0 is 0. So this is really complicated since it's a different angle than you're used to thinking about, and it's sine of that angle, sine of phi or phi. The reason we don't use theta for it is because we typically use theta for other angles. So please be careful about this. This is challenging to get right, and we'll talk in the next video about different interpretations of torque that might help you think through why we use this angle. One note, for torque we use this Greek letter tau, lowercase tau, which kind of looks like a T missing its head. You do typically want to make sure that this doesn't look just like T, since T is for time. So if we want to specify torque, we need to know a few things. One, the units are a Newton times a meter. There was a mistake here earlier. And what's important to note is that a Newton times a meter earlier was a joule, but in this case it's not a joule. So it's never correct to refer to a torque in units of joules, but the units are newtons times meters. So again, carefully define the angle phi, and we'll go through a little bit how to do that, but something that I want to point out is that the calculation itself is not going to provide the direction of your torque. The direction of torque can be clockwise or counterclockwise, and typically we use positive or negative. One is defined for, usually the book uses positive for counterclockwise and negative for clockwise, but you should always show your coordinates. Define on your work which way is positive and which way is negative. So let's go through looking at this angle. So here's a picture where we again have our wrench with our pivot point here, and forces applied in lots of different directions. So the 0 for phi is over here, right? This is phi equals 0. So in the case that you choose this one, right, pulling straight out exerts 0 torque because this is phi equals 0. Sine of 0 is 0. On the other hand, if we look at this one is 90 degrees, and this is actually maximum because sine of 90 is 1. This we would call an angle of 180 degrees, and sine of 180 is also 0, so this is again 0 torque. this, you could call this 270, or you could call this 90, depending on which way you want to measure your angle, and this is again maximum. So then, when we consider these final two things here, we see that if I exert my force this way, that would be rotating my wrench in the counterclockwise direction. So we call that positive. In this case, pulling down would try to turn my wrench in the clockwise direction, so this is negative. And this one down here is also maximally negative, this one up here is also maximally positive. So that direction, again, positive or negative, really only makes sense once you've tied plus and minus to clockwise and counterclockwise, and the convention of the book is for positive to be counterclockwise. Lastly, we need to define the idea of net torque. You've already met the idea of net forces, where you take all of your forces and add them up. And the same thing works here. You take individual torques, all acting on one object, and you add them up to find net torque. Now, one thing to note is that you must have your directions correct, so some of these might be positive and some of them might be negative. If some of them are in the clockwise direction, some of them are in the counterclockwise direction. So a few of the other things is that they all should act around the same axle. So when you go to calculate torque, make sure that you're always using the same pivot point for every single torque that you're adding together. The second thing is that the order here matters. You need to calculate the individual torques and then add them up. Don't think that you can take a shortcut by finding the net force and then somehow finding the torque from that. That doesn't make sense. Net force never relates to a net torque. That physically doesn't make sense. So in this case, each individual force would have to be thought about the direction it's applied at and the distance from the axle. So I get, for this one, I have this distance, and then I see that I have this angle. For F4, that is D4, and I see that's a right angle. F1, I call this D1. I know how bikes work, so I'm assuming that that is actually the same distance as D2. This is phi 1. And this is also then a right angle in D3. Note that this F axle, because it's applied right at the axis point, gives you 0 torque because the distance is 0. However, you would then have torques from each of these 4. You would need to get whether that is a clockwise versus a counterclockwise torque. You would calculate 4 individual torques and then add them up.